And at certain higher temperatures, right? This different materials can deviate from the straight line, right? So let's say at a different temperature range for different kinds of material, the resistive will vary different, right? Not like resistivity will not vary like this, but it will deviate or it will vary different. So for metals, right? So variation of resistivity for different, right? So let's say for metals, right? For metals, the resistivity varies like this is how the resistivity varies, right? So it varies like, and this is the temperature, this is the resistivity. And for alloy, like Nike, so the resistivity varies like so this is for alloys, right? This is the temperature which is increasing. And similarly, for the semiconductors, this variation is totally different. Right, so this is for semiconductors. And what we are seeing for both these cases, if we increase the temperature, then resistivity is increasing, right? But for
Yes, sir.
this semiconductors, we see that the resistivity will decrease if we increase the temperature. So that is the only difference between the metals, alloy, and semiconductor. So this is different kinds of variation for a larger temperature variation, right? If you have very larger temperature variation, then this would be the variation. This is for short range temperature, right? So this is over a period of time we can take this for a significant limit, right? We can approximate it linearly, but for a larger temperature difference, this would be the. Okay, you guys, please put it down, and then we will talk about the other. Okay, note down this right now. So I guess he
Yes.
has to oh, learn the words. And this they can ask in 1 mark, right? So they will uh, they will give you this type of question, and they will tell you that what kind of material is this. So you can clearly tell it that this is a semiconductor, right? They will give the resistivity, they will give the temperature variation, and you can identify that this is a semiconductor, right? Not a metal, not an alloy. This is the different kinds of.
Yes, sir. Done.
Okay, so the next topic is power and energy. What is power and energy? Right. So we know that from this second chapter. From the second chapter, let's say we have this resistance, right? And we have this supplied DC voltage, right? This voltage is fixed. This is some resistance R, the voltage is V, and the current is flowing, which is I. So we know that let's assume that this is a steady current, right? This is a steady current. This is not fluctuating. This is fixed. So if we have a steady current and this resistance and then this V, so we know that what would be the energy? Energy from the previous class. What was the energy? Remember it. Energy was Q into V, right?
Yes, sir.
Energy was so we calculated the work done, that was Q into, right? So we have a fixed potential, right? So work done would be equal to energy, and that is Q. And if we write this Q in terms of current and time, so this would be how much? We know that current is Q by T. So we can write this Q as IT. This would be how much? That would be IT, and this is V. So energy would be how much? Energy in the resistive circuit is VIT. And we can write this I in terms of resistance. So we know that V is IR. So we can write this I as V by R. Right. So if we write this as V and V by R, T, so this would be how much? So E would be V square by R. This is one form. This is other form. And we can also write this V as another. Right? So this V is IR and this is IT. So we can write this as I square R. So these are the three forms of energy that we can write. And from this energy, we can also calculate the power, right? Power dissipated would be how much? That is rate of doing work. So that would be energy by time, right? So this would be how much? Energy is VIT divided by time. So this would be VI, or we can write this as we can also write this as V square by R, or we can also write this as I square. So these are the different forms of power. Right. These are noted down, and then we will understand about cells. Right. Note it down, and we want me to.
Yes, sir, done.
This part also done.
Just last two. Yes, sir, done.
Now let us just about cells. Right. Before we do that, let us understand about this thing you already know, right? So I will just directly write this part, combination of resistance. This you already know. I will write this part directly, right? So there are series combination and there are parallel combination. So in the series combination, In the series combination, the effective resistance or equivalent resistance is simply R1, R2, R3, and so on. And for parallel one, this thing we have already moved from a 10th standard, so I'm just writing this part. Because this thing works. So for parallel case, 1 by R equivalent is 1 by R1 plus 1 by R2 plus by R3. This is for the parallel, right? And then we come to this part, which is, and there's this important question, right? So there's this important question, and this is about infinite, infinite series problem. What is this? So you have some resistance. So let's say you want to calculate the resistance between A, right? And this is, let's say, 1 ohm, this is 3 ohm, and this is B point. And then you have this again 1 ohm, 4, again 1 ohm, again 3 ohm, again 4, and again 1, again, and again ohm, and this continues infinity, right? And then they say that calculate the resistance from A. Then how should we proceed? What is the idea, or what is the thing that we get from this infinite series problem? What is the first thing that you guys see? Yeah, this is for you guys, for both of you guys. That's done. This question is, if you look at the question, what is the first thing that you guys
Sir, A and B.
yes, and B, and yeah, okay. So we see that block, this block is being repeated again and again, right? This block from here to right, from here to here, this block is getting repeated. So this block, then again this block, then again this block, then again this block. So this is being repeated again and again, right? Right, guys?
Yes, sir.
So then what we can do is that we can assume that the total equivalent resistance is R, right? So let's assume that this whole portion is R, and this is getting repeated again and again, right? So then we can write, if we block this thing, right? So if I put my hand on this part, so then again I get the same thing, right? If I hide this part, right? Let's say if I put my hand on this part, so then this part is again there. Again, the same thing goes on and on, right? Let's say if I hide this part, then again I see the same thing, right? Is it clear?
Yes, sir.
So then what I do is that I write this thing. So equivalently, I write this thing as I write this as 1, this as 3, this is as whatever 2 ohm and A and B, and then let's say I call it as R. Right? So that would be my equivalent resistance, right, guys? Is it clear?
Yes, sir.
Yeah. So my R equivalent, right? This would be equal to R, and I have to calculate this overall equivalent resistance, right? So I have considered, right? I have considered, I have taken, I have blocked this part, and I have considered all this thing as equivalent resistance, right? That is R, and that thing is being repeated again, right? Then I equivalently write this thing as this R, right? This R is being repeated again. This is the equivalent resistance that I have assumed. Is it clear, guys?
Yes, sir.
Okay, so now if I calculate this part, so now this has become easy. Now first I will calculate the equivalent resistance at these two points. Let's say C and D. So at C and D, this is 3 ohm and this is R ohm. Both are parallel. So at CD, R at CD would be how much? That would be 3 into R divided by 3 plus R, right? Is it clear? So this is 3R divided by 3 plus R. Is it clear, guys?
Yes, sir.
Now I write this thing equivalently as 1 ohm, then RCD, and then this 2, and then I put it as EN. So then RAB, that would be in series of all these combinations, right? So 1 plus RCD plus 2 ohm. And what was the RAB that I assumed earlier? What was the RAB that I assumed? That was R, right?
Mm.
Because this was the thing which was being repeated again, right? So I I hit this portion, right? I hit this portion and all the other things I called at R, right? And this is exactly like this whole portion. So this whole portion I assume that this is R. So this R is equal to 3 plus 3R by 3 plus R. So this is R, this is 9 plus 3R plus 3R divided by 3 plus R. This would be how much? 3R plus R square equals to 9 plus 3R, which is 1 3R we can cancel. This we can cancel. So how much is this? This is R square minus 3R minus 9 equals to 0. So then what would be the resistance that we get? So R would be minus B plus minus root D by 2, which is minus B is minus 3 plus minus root of B square, which is 9 minus 4, A is 1 and C is minus 9, right? By A is 1, so this is 3 plus minus, this is how much? 36, and 36 plus 9, because this is 9 plus 36 divided by 2. So this is how much? This is 3 plus minus root of 44 divided by 2. So I cannot have resistance to be negative. Solution would be how much? That would be 3 plus 44 by 2. And how much is 44? 44. This is 3 plus 6.63 divided by 2. Plus divided by 2. This is 4.8. So this would be the equivalent resistance. So whenever you guys get infinite series problem, then what you guys have to do? Did you guys get the idea? Yeah. Did you guys get the idea that what should you uh, this type of question?
Yes, sir.
So you'll have to assume that what part is repeating. Then you block that part and then assume that the total is R. So then you will get this thing, right? And you have assumed that this whole again is R, right? So then you solve these things and then you get a quadratic equation and then you solve this quadratic equation. Get a solution. Please note down this part and then we will start here, right? So quickly note it down. And if you guys have any doubts, please ask. In this question, we have to find resistance at the So this question is exactly like this, right? So let's say if you have a question like root of x plus root of x plus root of x plus root of x plus root of x goes to it, right? So whenever you guys get these type of question, right? So what you can do is that you see that this part is being repeated again, right? This part is being repeated again and again. So you can write this part as, let's say, y, right? So then you can write this y as root of x plus root of y, right? So this is the thing that you guys can use. This is exactly the same. It's this type of infinite series problem we do it. Okay, whenever you guys want me to scroll down, please.
Yes, sir. Done. Can you scroll down, sir?
Yeah, whenever you guys have noted.
Yes, sir. Scroll down. Yes, sir.
One moment, I have to pick up. Okay, guys, yeah. So then now we have to understand about the next topic, which is yeah. So the next topic is EMF, right? EMF of this thing. And this is not the force, right? This is why this uh, right. This is the next topic. And we have to remember that let's say you have a device, right? And you want a steady current in that device, right? Don't want, so let's say you have this household supply, right? And the house in the household supply, you guys want the fluctuation in current. You don't want any fluctuation, right? So the cell is that device which supplies a constant voltage, right? So it maintains the steady current state, right? This is the use of the cell, and what is the structure of the cell that you guys have already learned in your chemistry class. So what do you have in the cell? You have different things, right? So the setup of the cell is that you have electrolytic solutions, right? This is electrolytic solution, and then you have two rods, right? One rod is one rod, both are called electrodes, right? So one is cathode and one is anode, and this you have already done in chemistry class, so we will not focus it. And then you connect it with the resistor, right? So this is the experimental setup of a cell. And what is the purpose of this cell? So it provides a steady current in the circuit, right? And the value of the EMF of the cell is equivalent potential difference of electrodes at high potential with the electrodes at a lower potential. Right, so EMF is given by potential higher minus potential. This is the EMF of this. And this is not electromotive, so this is not a force, right? This is the voltage. So this is the voltage of this head, and it is generated by this electrolytic solutions. These have some ions, so the ions move, and then this completes a circuit, and then you get the EMF, right? So these are the two main uses of the cell. So it provides the EMF, and that maintains a steady current in the circuit, right? So these are the two main uses of the cell, and due to the electrolytes, the cell has some internal resistance. Right. So due to the presence of the electrolytes have the other forces involved, and they oppose the motion of the electrons. Right. So due to that, we have this internal resistance. So then we represent the cell. So geometrical representation of cell. How do we represent that? So geometrical representation. This is represented by two parts. One is the bigger one, the other one is smaller one. And then this has some internal resistance R, and then the current is flowing, which is I, right? So then we have this A point, and then this B point, right? So then we have this terminal potential difference, right? And what is the terminal potential difference? So terminal potential difference of cell, this is given by V, which is the minus of this IR, right? So this is the voltage supply that you get. So this is the voltage supply one gets, right? So the total voltage of the cell is E, but this amount is getting wasted in the internal resistance. So this much amount of potential you got from the cell. So these are the very crucial information of cell, and we will, yeah, then we'll do the next step. So please note down this thing, and if you guys have any question, please, please note it down. Yeah, whenever you guys want me to scroll down the screen, please.
Yes, yes. Update me. Yes, sir, done.
Then this part also.
Yes, sir, done.
Okay, so let's say that you connect this cell, right? So this cell is connected with the any other circuit which has some resistance. So let's say this is internal resistance, this is E, and then you connect it with the external resistance R, right? So and some current is flowing in this device. So then what would be the equivalent resistance? What would be that? That would be R plus this R, right? Because these are in series. And when you calculate this current, so current would be how much? Current is voltage divided by the resistance, right? So current in this circuit would be how much? That would be E divided by R plus R. This is uh, this is the current, right? And you have to remember this thing. So your if you are not connecting any resistive circuit to it, so then this would be short circuited, right? So if you connect this thing with itself, so this would be short circuited, right? And yeah, if the internal resistance is zero, then you have this maximum current. So these things we have to remember, right? This is when you connect an external resistance. So yeah, this is very, very important. And then we talk about the combination of cells. So again, there are two combinations. One is the series combination, and the other one is parallel combination. And what do we remember about series combination? So let us talk about this series combination first. In series combination, what is the preliminary idea that you have? Let's say you have this cell. This is E1, internal resistance R1. Then you have this E2, right? And then this internal resistance R2. And let's say you connect it with this one, right? So let's say you connect it with some resistance. This is a series combination, right? The negative one connected with the positive one, and then So can you tell me that in series combination, what is fixed? What is fixed and what is changing? Yes, guys. What is changing and what is fixed? In
So
series,
in series
yeah,
combination, what is changing and what is fixed?
yeah. So
Mm, which let me think.
current is same, right? Voltage is changing. That we have understood in the previous. So voltage is changing, right? If you have, let's say, two resistances, also, then voltage at this point and voltage at this point, this is different. If we have parallel thing, then voltage they are same, right? In series combination, voltage is different. In parallel combination, voltage is same. In series combination, current is same, but in parallel combination, current is different. These are the crucial information that we have to remember, right? Okay, so remembering that thing, we know that in here from here to here, right? From here to here, let's say this is voltage V1, and from here to here, let's say this is right. So total voltage that would be how much? That would be V1 plus V2, right? Right, guys.
Yes, sir.
And we know that how much is the so we know that how much is this V1 is. This is the terminal potential that we are talking about, right? So how much is this thing? If we look back the diagram, what was the terminal potential? This was E minus R, E minus IR, right? Right, guys? Is it clear?
Yes, sir. Sorry, sir. It's just my mind away. your
Yeah,
mic.
yeah,
Whenever I'm pressing it, it's sometimes I'm clicking on it, but it's not
oh
like
yeah,
turning
yeah,
it on for some reason.
oh yeah, it sometimes freezes, right? Okay, so V1 would be E1 minus IR, right? V2 would be E2 minus IR. So these would be the two cases, right? So let's say V1 is E1 minus IR1, right? And then this is plus E2 minus IR2, right? And this is okay. And if we write it this thing, so this would be E1 plus E2 minus I R1 plus R, right? And this would be V. And if we write this V in this form, so let's say V is E equivalent minus I R equivalent, right? This would be the overall voltage from this point to this point, right? From this point to this point, this is the overall voltage. And how do we write the terminal voltage? As E minus IR. So what I write is that let's say this is the overall EMF and equivalent internal resistance because my current is fixed. So that is why I have written this as overall voltage. Is this clear? Is it clear, guys? This would be
Yes, yes.
E equivalent minus I R equivalent, and that is E1 plus E2 minus I R1 plus R2. So if we compare this thing with this thing, if we compare the I term with this thing, so what we are getting? We are getting E equivalent, that is E1 plus E2, and we are getting R equivalent, that is R1 plus. So in series combination, the EMFs add up, right? Like this way. So we can make the effective diagram like this one. Effective diagram would be this E equivalent and then R equivalent and then this R. Right. So again, we can write this I as E equivalent divided by R plus R equivalent. That is again we can write the current in this manner. Right. And we have got E equivalent as this thing and R equivalent as this. So in series combination, the EMFs will add up, the internal resistance will add up. Is this thing clear, guys? Is it clear?
Yes, sir.
Okay, so similarly, what do we do in parallel combination? Okay, parallel combination. What we do? In parallel combination, the idea is that voltage is same. Voltage is same, but current is different. Right. So if we have this combination, and then let's say connected to some resistance. This is R2, this is E1, this is R1. So this is a parallel combination where all the positive ones are connected to positive, right? Negative ones are connected to negative. This is a parallel combination, right? And what do I know? I know that the current in this thing would be different. So current at this part would be different and current at this part would be different. So I know that my terminal voltage, this is E minus IR. So I can calculate the current as well. So current would be how much? Current would be, let's say I take this thing in the other side, and this is R minus. Then I take this negative sign in the other side. This is E minus V. And then I also take this R in the other side. So this is E minus V by R. This is E by R and minus V by R. This is my current. Is this thing clear, guys? Is it clear?
Yes, sir.
Okay, so now let's say the current flowing from this thing is I1 and the current flowing from this thing is I2, right? So can you guys tell me by looking at this example that what would be the current in first cell? What would be the current? Yes, what would be the current in the first cell?
Sir, I1 is equal.
What is changing? What is changing? Is V changing? V changing?
No, sir.
V is not changing. What is changing? E, R, are they changing? E is changing.
Mm,
That is E1, right?
yes, sir.
E is changing and R is changing. So these two are changing for I1, right? So we can write I1 as E1 by R1 minus V by R1, right? Is this correct?
Yes,
Is,
sir.
what would be I2? Yeah. What would be I2 if you look at in this term?
I2 is equal to E2 by R1 minus
R1, R1, very good.
R2. E2 by R2
And
minus V by R2.
yes, absolutely correct. And now we know that the total current that would be I1 plus I2, right? And this total current would be equivalent. That would be equivalent to how much? That would be equivalent to E equivalent minus V divided by this R equivalent, right? Clear? Is it clear?
Yes, sir.
So this is equal to I1, which is E by R1 minus by R1 plus E2 by R2 minus V by R2. So if we write E1 by R1, E1 by one side, and V part, so V by R1 and by R2. And I can take V common as well, right? So this is E1 by R1, E2 by R2 minus V and 1 by R1 plus 1 by R. This is equal to what? E equivalent divided by R equivalent minus V by R equivalent. And if you compare these two things, so what you can write? You can write E equivalent by R equivalent. That should be how much? If you look at the right hand side. So only this part is different. This part we have there. So this is E1 by R1 plus E2 by R2. Similarly, if we compare this term, right, so this term will give us 1 by R equivalent, and that is equal to 1 by R1 plus 1 by R2. This happens for the case of parallel combination. right? And yeah, again the total current in the circuit would be how much? That would be E equivalent plus that would be E equivalent by R plus R equivalent. So that would be the okay. But you guys please put down this part. And if you guys have any question, please tell me. Right, this part. Yeah, I started with this part. Right. Please note it down. And if you guys have any question, please tell me. We'll end the class at 10:40, which is almost right. 10:30 is
Sir, it's 8-7 here. So,
yeah. So after 3 minutes, I have to end this class.
okay, sir.
And you guys please revise this part, right? Otherwise, it will be very difficult to understand. So just you have to remember that in a series combination, current is same. In parallel combination, voltage is same. And we will do a couple of questions. So in the next class, this chapter would be over because we have Kirchhoff law and Wheatstone bridge. These topics are yes. Whenever you guys want me to scroll down, please.
Yes, sir, done. Yes, sir, done.
Already. What about you, Mir? Is the idea that we took that what would be the current, and then we applied it, right? And then we calculated the overall current, and then we got
Yes, sir, scroll down. Yes, sir, done.
done. Okay, what about you, Mir? Done.
Yes, sir.
Yes. Okay, so let's stop it here and see you guys in the next class, right? Couple of questions from this one, and then this would be right.